us, see, the customer will come and or approach and ask you that this is the task I need. You please design a robot for me. See, this is what I need. See, from this point, the object is to be picked, and from this point to this point, the object is to be placed. Can that be done? Okay. So if you are not into kinematics and dynamics part of robots, what will happen is, see, only by trial and error you design this robot, right? But then no, you won't be able to say that, okay, whether this robot will be able to move from the desired point which I am talking about to the desired goal point. Okay. So this is the first point you need to consider, whether I can design a manipulator which is of the which is required, or depending on the requirement, can I design a robot? That's the first question. Okay, whether without knowing kinematics and dynamics, will you be able to do that? That's the first question. And now if you look at another scenario, okay, students are building robots like this, and they are participating in many competitions for line follower robot. So this is basically line follower robot. So you could see that this robot will be capable of following a line, right? Maybe while moving, it will move through this path also. Okay. Okay. When the students start working on robotics, they can take up these kinds of works. Well and good. But the thing is that the only thing we want? See, you have a fixed line like this, and over that, the robot has to move. Okay, that is not the case, right? So the situation is that, imagine that, see, I don't know where all these participants are sitting. Some may be at home, or some may be at their respective colleges. So you all are sitting in a particular room. Okay, that is for sure, right? So can you imagine a line which is just near to you, parallel to your table, and can I ask, see, I'm building a robot, and can I ask the robot to move through that line? Okay, or I say, I will be drawing a circle. So physically, I won't be drawing. See, virtually, you can imagine a circle which is having 1 meter diameter, and can I move the robot which I built through that circle, the virtual circle which I imagined? So can I do that? So definitely, we'll be succeeding in doing these kinds of stuff. But we must, as engineers, we should be able to move the robot from whichever destination, whichever start point to the whichever goal point. Okay, so that is what we should try for, right? And this is second scenario. Generally, students do this as a very fantastic project, but see, I'm not saying that this is bad, but for a beginner, definitely this is good. But definitely you should try to build robots which are capable of moving in a virtual line or a virtual circle that's wherever I desire, I will be able to move the robot, right? Without the markings of a white line or a black line. And this is another trend I could see. Okay, so you see all these I am talking from students' perspective because all of you are teachers. See, and now what we see in some of the projects is that, okay, they say that, okay, I have built a robot which is capable of obstacle avoidance. Okay, so what we see is that, what we see in those kinds of general trend, always there are exemptions. For example, suppose the robot is starting from point A. Okay, maybe near your, see, you are sitting in a room. So the robot is starting just by your side, and we see the robot has to reach the the entrance, okay, or the drawing room of your home, or the HOD's room of your department. Just imagine it is starting from near your chair and it is going towards a destination, which is maybe like drawing room or kitchen, wherever, or some other room maybe. So that is a practical scenario. So wherein, see what the robot has to do, the robot will be moving like this. And suppose if there is a table or something at this point, what the robot should do? The robot should avoid this obstacle and move to the destination. This is what the robot should do. But what generally the robots, our students built are doing, so what it does is, see, it will be moving like this. It will be moving like this. And when it sees sees an obstacle, the algorithm will be saying turn right or turn left. Done. So, and they claim that it is an obstacle avoidance robot. But is that the thing which we need in a practical scenario? Practical scenario means there'll be obstacle, it has to avoid the obstacle, there'll be some other obstacle. So that should be avoided, and then finally it should reach the goal point, right? So that should be so it can avoid obstacles. So simply by turning left and right means the robot will be randomly moving, right? So how do we achieve all these things? Okay, how do we achieve all these things? Or for example, see, in this COVID times, I think many colleges or many among you might have built robots which are deployed in hospitals and all, right? So maybe deployed in hospitals. So maybe see the robot will be starting from a particular start point, and then it has to deliver food to room number 1, deliver food or medicine to room number 1, or maybe room number 2, or room number 3, like that, right? So there'll be different rooms and the robot has to do that. So when, suppose if it is moving like that, and if it is finding an obstacle, if you say that, okay, turn left or right, will the robot be able to reach the destination, or will be able to do the complete the task? No, right? So when we are designing robots for obstacle avoidance, we need to keep all these things in mind. So it should be realistic scenario. It should not be designed for turning just left or right, but it should be able to do this task. Okay, so generally, suppose you have this hospital scenario, okay? This hospital scenario, right? So how do we tackle this problem? So can one among you say, like, suppose I have a start point and the robot has to deliver medicines to these 4 rooms, just imagine. So which robot you will prefer? Can anyone say? Basic configuration. Please unmute mic and speak so that. Any suggestions? Will you go for a robot with 2 wheels, 3 wheels, 4 wheels? How many motors you will choose? Can anyone? Dr. Deepa, there are any comments in the chat box?
No, ma'am.
No one is responding?
Not yet.
Ma'am, there is a comment 3 wheel.
3
wheels. Okay, 3 wheels. Okay. So, so I would like to know, like, how many motors then? How many wheels are driven by motors and how many are supporting wheels?
Answer has come, 2 motors.
2 motors. Yes, 2 more. So the suggestion is good actually. So there are two motors. So suppose if there are two wheels like this, see this is one wheel, so there should be a motor here, motor 1. And for this wheel also there's motor 2. And this is a caster wheel maybe, right? So that is maybe the suggestion. And another option is that there can be two wheels at the front for supporting, because you will get a better stable configuration. So you can have two wheels at the front also as supporting wheels. So that will be the best configuration. And suppose if these are the two motors you have, how do you control that robot to reach these destinations? So I just want to know your initial thought. It need not be an expert answer. Just a random thought is fine. So that's what I wish to know also. See, just imagine there's a two-wheeled robot which is being moved. Three-wheeled robot which are being driven by two motors, and it is driven to move through this path, right? See, it has to start from here, maybe from the central room or storeroom where the medicines are collected, and it is to be delivered, or maybe food. Can someone answer? Okay, see, how will it move? How do you direct it? Will you use joystick, or can it be autonomously moved? Come on, friends. Otherwise, it will be monotonous.
Ma'am,
Yeah.
we can use either joystick or it can be autonomous. That depends upon the path which is we need to follow that.
Okay. So see, if it is too much crowded, maybe you can think of joystick based control, and but otherwise, if it is maybe you can go for autonomous driving also, right? So in autonomous driving, so can you drive the robot? So generally in joystick, no, what you do is just you'll be driving these two motors at maybe at constant speed, or if it needs turn, so that will also be given by a command. Okay, so that is the simplest way of controlling that robots. So my question is, see, you have the left wheel and the right wheel, right? Left wheel and the right wheel. And the right wheel, okay. So my question is, see, the left wheel will have a velocity. See, I am denoting that as some omega L, and the right wheel will have another velocity, omega R, okay. So my question is it possible to drive this robot by means of, see, if you know what should be the left wheel velocity and what should be the right wheel velocity, so that I can see what should be the left wheel velocity and right wheel velocity at each point since time, so that I can move the robot from this point to this point, and from here to here, from here to here, from here to here. So see, if you are trying to build a robot in an autonomous mode, no, finally you should be able to find a profile of, see, at each instance of time, you should try to find omega R and omega L profile. So as engineers, so this is what I suggest, okay? As engineers, we should try to drive robots in this way, okay? So you should know what should be the left wheel velocity and right wheel velocity, so that we will be able to drive the robot from the start position to the goal position, avoiding obstacles, okay? So if you have to do in that way, right? See the tasks, which are the tasks I was mentioning? The task, the first task wherein I will decide the start point and I will fix the goal point. And can I design a manipulator which is capable of picking the object from A and placing it at B? So can I design a robot which is capable of moving through a line or a circle, even though it is not marked by in black color or white color? can I move this robot from a start location to goal location, avoiding obstacles? And can I find what should be the profile of left wheel and right wheel velocity so that I can reach the respective destinations? If yes is your answer, then only you need to know all these things. And if you wish to do all these tasks by trial and error, I think, see, all as engineers, we must try to do in that way. So that's my thought. So you must be able to do those kinds of tasks rather than trial and error. So if you wish to do tasks in that way, we should know a lot of things like the kinematics, which some of you may be knowing, or maybe I think in subsequent sessions that will be covered. You should be also you must also know about what is known as dynamics. See, these are the two common words, very common words, which you hear when you study about robotics. So, kinematics and dynamics. So, what is kinematics? So, that means it is analytic study of geometric motion of robotic arm without considering forces and moments. Okay, without considering forces and moments, if you wish to analyze the motion of a robot, then this is what you need. But suppose if you wish to include the forces and moments acting on that robot, then you should you should try to derive the dynamic equations for the robot. So earlier I was talking about that case, the robot case, a robot in a COVID ward or in a hospital for assisting the patients. So suppose if that robot is being used for just medicine delivery alone, right? So then the payload which is to be carried by that robot will be very less, right? Maybe less than 1 kg. So in that scenario, maybe knowing the kinematics is fine. So you don't need any force and moment analysis, torque analysis in that situation. But suppose if the payload is more, okay, suppose the robot has to carry food, so many food packets, some 20 food packets or 50 food packets are to be carried, the payload is high, then you must go for the dynamic analysis, right? So depending on the context wherein, okay, the robot is being used, see, so in this case also, see, if the robot is picking the empty bottle, maybe with the kinematics, you will be able to proceed. But if it is full bottle, it is filled with water or the payload is very high, then no, you must go for a dynamic analysis. So this is a requirement. So if you wish to go for trial and error method, no need to learn kinematics and dynamics. But if you wish to design a robot as an engineer, definitely you must know these kinematics and dynamics. Okay, so there are some other basic characteristics also which are related to robotic manipulators, like PPP configuration, which is prismatic configuration. It is based on the type of joint which the robot is having. And next is RPP, this is revolute prismatic. So RRP, RRR, which is the articulated robot, and SCARA robot. These are very famous robots, the standard configurations of robots which are used in industries. So those who are about to learn robotics are already studied, so they'll be knowing about this. So in addition to that, robot specifications. So for example, suppose I am planning to design a robot for a particular task. How many degrees of freedom it should have? Does the end effector of the robot need the yaw motion, pitch motion, roll motion? Okay. So see all these, and what should be the speed at which the end effector should move. See, all these should be fixed, and then you need to start designing. Or suppose if you see nowadays, no, this manipulator design part, no, rarely people are doing, because all the standard configurations in the industry are available. So you will be able to choose whether you need a rectangular robot, or a cylindrical robot, or a spherical robot, or an articulated robot, depending on the work envelope which the robot is having. Work envelope means it is the locus of points in 3D space where the end effector of the robot can reach. Okay, so based on that conversation, suppose if you are planning to design a mechatronic system, then a robot will be one of the component of that, and you should know, okay, does my robot need a rectangular work envelope, or a spherical work envelope? So depending on that, you will choose this particular configuration, right? And see, if you wish to design a robot, you should also know how to represent position and orientation of robot, mainly in case of manipulators. So if that is to be done, you should know about what is homogeneous transformation matrices. What are homogeneous transformation matrices? So those who have studied robotics will be knowing. So then only you will be able to represent the position as well as orientation of a robot. Okay, and if you are doing this problem, then you will be using Dynavit-Hartenbed algorithm for deriving the kinematic model. Okay, so inverse kinematics means it is actually, see, forward means see, you know the joint angles, and finding the end effector position is forward kinematics. And inverse means you know the end effector position and you find the joint angles, so that's the inverse kinematics. And dynamics, as I was mentioning already, see, it is analysis of motion of robots considering forces and moments. And see, as an engineer, you should also know in which context you should go for kinematics and in which context you should go for this dynamics part. Okay, and in addition to that, you should know about the trajectory planning of robots too, so that you will be able to plan the path perfectly for the robots. So if you are having any queries, you can ask. So next comes, see, the topic of the discussion is actually modeling of robots, right? So as I was mentioning, see, the first part when you take up a project like that is the mathematical modeling part. Okay, so mathematical modeling is in that way very, very important, because you decide that you are going to design a robot by using the concepts of engineering rather than trial and error. Okay, so that's why we need this model. So it is a representation of essential aspects of existing system or the system to be constructed, which represents knowledge of that system in usable form. Okay, so it can be statistical models or differential equations or game theoretic models. So mathematical modeling problems are often classified into black box or white box models according to how much a priori information is available for the system. A black box model means there is no a priori information available. A white box model means some information is, so where all the necessary informations are available. Okay, so in short, what you need is, what is the relation between the input which I am giving to the system and what is the output I am getting from the system. So I need to have an idea of that whenever I am considering a robotic manipulator or a mobile robot or whichever system I am planning to work with. Okay, So for example, if you consider a car, okay, so many of you maybe see, all of us are driving cars. So can anyone tell me what are the inputs? See, what I'm telling is that I need to get a mathematical model, right? So if you consider, see, car is a very simple example. So if you consider car, you are driving, what are the inputs I am giving to my car while I am driving? What are the inputs I am giving when I am driving? Because see, what I was telling is we need a relation between the inputs and the output. Okay. So can anyone say that? Inputs. Dr. Deepa, any answer there?
Yes, ma'am. Acceleration is coming. Accelerator.
Yeah. Okay. Accelerator is one of the inputs. Then only accelerator.
And again, steering, judging the path.
Yeah, accelerator is one input, steering is another input, and then
judging the path is there, right?
No, judging the path, okay, maybe that's the sensor information. No,
Yeah.
if you consider the car as a system,
Fuel.
Cars.
One person is given fuel.
No. See, I won't be giving fuel, no. See, fuel is already there in the fuel tank.
Brakes.
Brake. Yes. Brake. Yes. So these are the three inputs which I see. Fuel is already filled there, right? So the inputs which we give while driving are, see, you press the accelerator pedal, then sometimes the brake you apply. Yes, any questions?
No, ma'am.
Okay, so the accelerator pedal, the brake, as well as the steering, right? So these are the three inputs which are given to a car. Okay, and what are the outputs which I am getting? So the output I am getting is, see, while I am driving the car, I'll be getting, I can say my car will be taken to a particular X position, my car will be taken to particular Y position. Maybe in Indian roads, you will have some Z position also. But in general, I can say, okay, X, Y, and some heading angle or orientation, which is theta. Okay. These three are the very basic inputs, very basic outputs I can talk about a car which I am driving. Or you can also consider a little more advanced model wherein x dot, y dot, and theta dot also as the outputs from a car. Okay, so I was taking a familiar model because now all of you are aware of this. So I am giving, while driving, I am giving accelerator, brake, and steering. And my car is getting some desired x position, y position, some x and y, x of t I am getting, y of t I am getting, theta of t I am getting. And in addition to that, I'll have some x dot, y dot, and theta dot. Okay. So can I have a relation between this input and the outputs? Okay. So can I have a, just a minute. Okay, sorry. I was just familiarizing you with the model which all of you are aware of. Now coming back to the model which we know, see, which I was talking about. See, this is a mobile robot. See, if this is a mobile robot, what will be the inputs to this robot? So it will be the velocity. There are two motors there, so I need to give velocity to the left wheel and the right wheel. So these are the inputs which I'll be giving to the robot, and what will be the output? The output will be X position, Y position, and theta of the robot, right? So in this case also it's like that. So depending on how many motors, so those many motors should be driven by, motor speeds will be the input and output will be the X, Y, and theta position of the robot. So in this case, what are the inputs? So in this case, there are how many motors are there? So corresponding to that, so you should know what should be the speeds or the position of the joint angles, the motor to be driven, and the required output is actually the end effector position, right? So whatever is, whichever robot you are planning to design or you are working with, you need to have this kind of thought. Okay, which are the inputs? Which are the outputs? Can I get a relation between these two? Okay, so if you have that question, you will be able to end up with, so from basic physics, you will be able to end up with a differential equation or a transfer function or a state space model. Okay. So maybe I think those who belong to electrical or electronics branches will be familiar with this. I'm not sure whether there are people from mechanical background are also there. Dr. Deepa, people from mechanical background are also there?
Yes, ma'am.
Yes. Okay. So they will also be, I'm not sure whether they'll be knowing. So state space model also, it's actually, you'll be able to represent the system in terms of a set of first order differential equations. That's it. Okay, for example, don't think that we need to start with very big equations or complex equations for modeling the robots. We can start with very simple equations. So can anyone from mechanical say about this? Are you familiar with transfer functions or state space models?
Anyone from mechanical engineering?
No. Okay, so generally, suppose if you have an object which is being, suppose it's kept on a
there is a
table.
comment in the chat box saying that they have studied a bit.
Okay, they studied a bit. Okay, so I don't have to explain, I think. So okay, so just in a minute or so, I'll try to explain this. Suppose if I am pushing this block, if I'm pushing this block by applying a force F, it will have a displacement x of t, right? So how do we express how do we write the equation of motion of this block? So I'll be writing the equation of motion as mx double dot plus bx dot plus kx is equal to f, or f, see, all are functions of time, right? So where m is the mass, b is the viscous friction coefficient, k is a spring constant. All of us are aware of this, right? So this is the basic differential equation I'm talking about. For any system, you should be able to write like this. And transfer function means you need to identify. See, if you look at this system, which is the input? Input is f. Okay, it's f of t actually. And what is the output I am getting? It is a displacement, or I can also talk about x dot of t, the range of displacement. So transfer function means it is a Laplace transform of output to Laplace transform of input. If you try to find, that is actually the transfer function. What you need to do is you just find the Laplace, convert to S domain and take the ratio. So if you write like this also, you are getting a relation between the inputs and the the inputs is this, the input and the output. If you're writing this also, you'll be getting an expression ms square plus like this. So you'll be getting a relation between the input and the output. Similarly, so you will be able to represent the same as state space model. So from this, suppose if you look at this equation, it is a second order system. So for a second order system, we will take two states, okay, two states. So I can take x1 and x2 as the states of the system. So I'll write x1 dot is equal to x2 and x2 dot is equal to, I can take from this, right, x double dot is actually x2. So it will be 1 by m f minus, like this, you take this to right hand side so that you will get an expression for this. And so it's writing the equations of motion of the system as in this form, like x1 dot equal to x2 x. So it's set of first order differential equations. So writing like this is referred to as state space model. Okay, and similarly you need to decide, suppose if you wish to control this block, what is your desired output? If it is just position alone or velocity, what is required, you need to just define that there. So if you completely define like that, we call this as a state space model. So what I mean is, you need to just have an idea of input output relation either in any of this form. It doesn't matter. So you need to just apply the basic physics and try to find the relation. So some will be having some properties in some equations, some systems you will be able to represent like this, which are linear systems, but some systems may be non-linear. So then you will be able to represent like this only. So you need to know what is the output. Okay, I need to consider only car's position x, y, and theta alone, or I need x dot, y dot, theta dot of the car. Whatever, see, you need to decide because you are the engineer, you are going to design the system, right, in that way. So now I'm going to take a very simple configuration for modeling. So see, I told you the necessity of modeling. So without trial and error, if you wish to work with robotic systems, definitely you need to go with the mathematical modeling in one way or other. So I'm taking a very simple configuration called a differential drive robot, wherein there are, see, this is a basic this is a top view of a differential drive robot, wherein you can see two wheels which are driven by two motors. See, like this, two motors which are driving the two wheels, and there's a free turning wheels, which is for, this is for supporting. We call it as a caster wheel. See, so that is just beneath this. So how we can move this vehicle forward? Suppose if this vehicle has to move forward like this, suppose it has to move with a velocity v. Okay, so what I'll do in a straight line, if it has to move, what I'll do is I'll drive this. This is a right wheel velocity and this is the left wheel velocity. So I'll be giving equal speeds. Omega r will be equal to omega l, and the vehicle will be moving like this. And suppose if I wish to take a left turn, what will I do? Left turn means omega l will be less than omega r. Okay, so it will be taking a left turn. So omega l will be greater than omega r. So sorry, omega r, then it will be taking a right turn. So, so this is a very simple configuration to start with. See, so once you are confident with modeling of this, you will be able to start modeling. Especially mechanical engineers are very good in modeling part. So this is a very famous configuration which is being used in Pioneer, Ragwarir, etc. And so what I'm trying to do is I am trying to model this robot in a very simple form. So as I was mentioning, no, you don't need to start with a very complex equation. Just start from with a very basic equation which reflects the behavior or the relation between the input output. Later you add on to that. all the effects or the dynamics also you will be able to add to that system. Okay, so what I'm going to do is I'm going to consider this robot as a point object. See, I told you, you just consider it as a very simple system which is moving with the linear velocity v and angular velocity omega. What is that? When I am driving my car in a straight road, it will be having v alone, right? It will be having v. V means it's the linear velocity. And when the car is taking a left turn, so it will be having v as well as omega, right? So when it is taking turns, left or right turns, it will be having v as well as omega. If it is having omega alone, means it's fully turning, right, on its own. So generally in car we won't be doing that. So it will be having a v and omega. So if it is considered as a point object, and if I say that if I mark an axis in this direction as x, and if I mark in this direction the axis as y, and this as the orientation or heading angle of the robot, I will be able to write that the rate of change of x, which is x dot, it will be equal to v cos theta, right? V cos theta, because that's the horizontal component of distance which will be covered by the robot if it is moving with a linear velocity v, and y dot will be equal to v sine theta. Okay, and theta dot will be equal to omega. Okay, rate of change of angle will be equal to theta, heading angle will be equal to omega. Okay, so this is very simple equation which gives the relation between the inputs and the output of the robot. In this case, what is the input I am giving to the robot? So if I am getting this relation, v and omega are the inputs to the robot which I am considering. In this particular case, the linear and angular velocity, and what are the outputs I needed? The outputs are x, y, and theta, the desired values I have to drive, right? So you need to first identify, see, how can I get a very simple relation? If I take which all inputs I can get simple relation, then you try to expand. Okay, so I have taken v and omega as the inputs to the system and x, y, theta as the output of the system. But the thing is that, see, when I consider this robot, see, generally, if you take v and omega as the inputs, see, that is, so you won't be directly able to control, right? So what we need is the right wheel velocity and left wheel velocity instead of v and omega. So if I can get the relation between, see, I was telling, see, I know v omega, and from that I will find what should be this. Instead of that, if I can get omega r and omega l, then it is, see, I am in a better position. It is easier for me to control the robot, so that, see, left wheel velocity I know, right wheel velocity I know what is the corresponding xy theta position, so that it is easier to control my robot. So what I'll do is I will just try to get a relation between this v as well as v omega and left and right wheel velocities. Okay, how can I get that? Okay, so we know that when the robot is moving in a straight line, so the linear velocity will be proportional to the average of these two velocities, right? So see, if omega r is the right wheel velocity, omega l is the left wheel velocity. So you can say that v is r omega, generally we say, right? So the effective omega will be equal to omega r plus omega l by 2. So I can say v is equal to, so what I got? I got a relation between left wheel, right wheel velocity and the linear velocity of the vehicle. And similarly, if you consider, what we need is, we need the relation between the angular velocity and the right wheel and left wheel velocities of the vehicle. So just if you apply common sense, I can say that, see, the angular velocity will be proportional to the difference in speeds of right and left wheel velocities. Okay, so this you can derive from these basic equations. If you refer to these equations directly, you will be able to derive this equation. Okay, so what I was trying to do is, I was trying to get the relation between left wheel, right wheel velocity and the linear velocity of the vehicle, right wheel and left wheel velocity, and the angular velocity of the vehicle. So I got the relation between them. So if I substitute that in this equation, see, I have the expression for V, I have the expression for omega. When I substitute, now I got a perfect relation between the inputs and the output. So this is what I need to start with. Okay, a very basic relation between the inputs and the outputs. Okay, so see, as this is a very simple example and it's easy to follow, I have taken this example. So ultimately, for any system, you should try to do in this way only. Okay, so but see, for the robot which is being used in a hospital case also, you will be able to use this same relation, wherein in order to get the desired x position, y position and theta, you will be able to drive the wheels to required right and left wheel velocity, so that it will be able to reach the destination. So this is an illustration of the power of mathematical modeling of a very simple robot. Hope the message is clear. Any queries or any doubts?
Ma'am, nothing so far, ma'am.
Yes. Okay. So till the last slide, I was just talking about very simple relation between the velocities, right? The left wheel and right wheel velocity and the x, y, theta positions of the robot. But see, in the same robot which is being employed in hospital, if the payload is more, okay, the payload to be manipulated is more, then you won't be able to work with this model, right? This is very simple model which gives what should be the left wheel and right wheel velocities, so that I will be able to reach the destination. Okay, but suppose if the robot is carrying 10 kg payload, 20 kg payload, then I may not be interested in this model. Anyway, the basic part I need this, but what I need will be the dynamic model. Okay, so dynamic model, so there are different methods to derive at the dynamic model of a robot. So here also I'll be taking a very simple example for dynamic modeling. So there are different methods. One of the simplest method is called Lagrange-Euler method, which is energy-based approach. So a Lagrange function is a scalar function, and it is defined as the difference between kinetic energy and potential energy of a mechanical system. Okay, so generally Lagrangian is defined as L, which is equal to kinetic energy minus potential energy. And the formulation is based on set of generalized coordinates to describe the system variables. Okay, so in this case also, so this is basically the Lagrange equation. Once you find the Lagrangian for a system, you find dou by dou q dot of L, so dou L by dou q dot, and then you find d by dt of that. So d by dt of dou L by dou q dot minus dou L by dou q equal to F, which is the generalized forces acting on the system. Okay, and what is Q? Q are the generalized coordinates, and if you consider a robotic manipulator, Q means it will be theta 1, theta 2, theta 3, like that. And if you are thinking of a mobile robot, which I was talking about, a differential drive robot, it will be X, Y, theta. Okay, so Q means the generalized coordinates, and F is the generalized forces which are acting on the system. So when you, from fundamentals, when you start deriving the model will be in this form. Okay, it will be of the form M of Q, because it is this M of Q will be a function of Q. See, if you consider a robotic manipulator, at any point of time, that inertia matrix will be dependent on the position of the joints. So that is why, because it is written as M of Q. Okay, so into Q double dot. So Q means theta 1 double dot, theta 2 double dot, theta 3 double dot, like that. And then we have VQ dot, which is a centripetal and Coriolis matrix. So I'll be just saying that in general, it will be having the inertial force components. It will be having centrifugal or the Coriolis force components, and the gravity vector component, and also the input vector. Okay. And see, generally when we consider the movement of a block, what we say? See, I was telling the equation mx double dot plus bx dot plus kx equal to f, right? So there, no, you are having ma, right? Ma part only. But as a robotic manipulator, no. So the one joint is moving. See, when you consider the movement of our hand. Okay. So when, suppose if I have to take a glass of water, just imagine. I have to move my shoulder joint, I have to move my elbow joint and the wrist. 3 joints are simultaneously moving, right? So see, at all these, so there will be the effect of motion because of shoulder joint, elbow joint, as well as the wrist joint, right? So when all these are coming to play, when all these forces are coming to play, so there will be this component, which is called the centripetal and Coriolis force matrix, which will be generally in this form, and there will be gravity vector and there will be input vector also, ultimately. Okay, so how do we get that in a very simple robot? See, I am just telling you very simple cases because I just want you to convey this message. So this is the way you need to do for any robot. Okay, so if I start with a very complex case, no, you will think that it's very difficult. Okay, so when you start modeling, taking into consideration very simple aspects, you will get a very simple model, and then try to add the complex dynamics into that, so that you will be able to solve that problem and you will be able to design those systems as well. So I'm considering the dynamic model of a 1 degree of freedom robot. Okay, 1 degree of freedom robot. If you consider, what do you mean by degree of freedom? Degree of freedom means number of independent movements possible. Okay, so if you look at this robot, see, this is having only one link. Okay, this is having only one link, and it is having a motor attached to this. Okay, so when this motor is moving, this robot will be having a joint angle theta as marked here. Okay, so that is why it is defined as a 1 degree of freedom robot. So this is basically an inverted pendulum model, which we call as the 1 degree of freedom robot. Okay, so how do we model this? Using Lagrange-Euler equation. So what we need is, you need to find the kinetic energy and potential energy. Okay, so how do we find the kinetic energy? kinetic energy is equal to, so we see as there are linear and rotary movements. So what we have to consider is we need to take two components. One is half mv square and other is half I omega square. Okay, so we know that for a thin cylinder of mass m, the moment of inertia is ml square by 12. Okay, so this I should be equal to ml square by 12. So so if you substitute, see it's half mv square. We know that v is r theta dot, right? So r means, see, from this point the distance is L by 2. So L by 2, so it's r theta dot. So it is L by 2 theta dot the whole square plus half into I is substituted, and omega means it is theta dot square. So when you rearrange, you will get kinetic energy. And similarly, you need to write potential energy is mgh. H is actually L by 2 sine theta. So you will get mg L by 2 sine theta. So the Lagrangian is kinetic energy minus potential energy. Then you need to apply the Lagrange-Euler equation. So first you need to find dou L by dou theta dot. So dou L by dou theta dot will be, see, if it's theta dot square, so 2 theta dot. So here no theta dot is not there, so this term is not required. You need to represent like that, and then you need to again differentiate that. So when you differentiate, you will get like this, and then finally expression for tau is like this, so that you will be getting the final torque equation for the motor like this. Okay, so when you see, we have seen this scenario is 1 degree of freedom robot. So it is having only one motor, right? So what you got is the expression for τ1. Only one torque is there in terms of all these parameters. Okay. Suppose if you are having 2 degree of freedom robot, so that means there are 2 joints and these joints will be driven by 2 motors. So then if that is the case, you will be getting expression for τ1 as well as τ2. You will be having the equations like that. And if it's 3 degree of freedom robot, similarly you will be having expression for τ1, τ2 and τ3. So that is the case of a manipulator. But suppose if you have a mobile robot, specifically a differential drive robot, so when we took the kinematic model, the inputs which we considered are right wheel velocity and left wheel velocity. Okay, but when we try to derive the dynamic model, see, you will be getting the expression. You will be getting the expression for τ1, and you will get an expression. You will get an expression for τ2 also, because in a differential drive robot there are 2 motors, right? So for the actuating mechanism or the inputs are τ1 and τ2. So you will get an expression for that. So at each and every instance of time, what should be the value of theta, everything we know. So we will be driving the robot so that the required torque is applied to the motor so that it will be able to deliver the heavy payload which it is carrying. So if it is an omnidirectional robot, then there will be 3 wheels, right? Generally. So in that case, so if you would have taken the kinematic model, it will be omega 1, omega 2, omega 3 are the inputs. So when you take the dynamic model, it will be τ1, τ2 and τ3. Okay, so that is the difference between a kinematic model and a dynamic model. Okay, so when the payload is less and the speed of operation of the robot is that's when the robot is moving very slowly, then we can manage with the kinematic model itself. Depending on the requirement, you have to use the forward or inverse kinematics. And when the payload is high, definitely you have to obtain the dynamic model, and then only you will be able to proceed. Okay. So otherwise, what happens is that maybe you have to see the robot has to move from one particular point to other. What you do is, by trial and error, you try to find some of the values for the left and right wheel velocities and drive it so that it reaches the destination. Okay. Hope up to this everything is clear. Any doubts, anyone?
Ma'am, nothing so far, ma'am.
Okay. So, see, when we are studying about robots, see, once the modeling part is done, see, I have just taken very simple examples. So whichever is the robot you are working with, try to get the model in one way or the other. So once you get the model, the next part which we generally do is the path planning of robots. Okay. So there is actually standard definition for a path as well as trajectory, which I have given in the slide. See, a path is a locus of points, either in joint space or Cartesian space, to be traversed by the robot to execute the specified task. And trajectory means, in addition to this information, the time information will also be given. Okay. For example, see, in this case, no, it's just locus of points. So locus of points means if you consider a differential drive robot. So if you consider differential drive robot, you say that x, you have a vector position of x, you have a vector position of y, and you have a vector position of theta, only that much. But trajectory means it is actually x of t profile. You have the x of t profile, you have y of t profile, you have theta of t profile. Okay. So, see, this is the path to be traversed. Okay. So, in order to traverse this path, what should be the, say, suppose if you take a differential drive robot, what should be the right wheel velocity profile and the left wheel velocity profile, so that I can follow this path, right? Or if you consider a robotic manipulator, then it will be the end effector position. The end effector, maybe the end effector x of t, y of t, z of t. Okay, and then you need to know, see, what should be the joint angle profiles, right? So it will be function of time, theta 1 t, theta 2 t, theta 3 t. So it will be as a profile, you should be able to know that. So then only you will be able to drive the robot from the start point to the goal location. Okay. So so if you wish to make it autonomous, definitely you need to know the input-output relations represented either as a state space model or a differential equation or a transfer function, so that you will be able to plan a path from the start point with the desired orientation. So start point with the initial orientation to the desired point with the desired orientation. Okay, you will be able to move that. So this is actually a path planning scenario you could see where the robot is being moved. So in all these cases, the time information is also required. Okay. So generally in path planning of robots, the common method which is being adopted is called the Dubin's path. which is being used in wheeled robots and UAVs, etc. So here the examples, see the situation is, see for example, just imagine your car is parked like this, or your car is at this position, and just imagine the car has to move to this position with this orientation. Okay, how do you achieve this? So just imagine that you are not using the reverse gear, only with forward motion. How do we achieve this? Okay, so similarly, when you are moving a robot to achieve these kinds of tasks, see, suppose the robot is at this position, it has to come to this. So generally, we won't think of moving the robot in the backward direction. So we will just assume that it's moving in the forward direction itself. So see, this is one of the options for parking the vehicle like this. So if you look at this, see, it is taking a circular segment here, then it is taking a straight line path, then taking a circular segment, and it's parking the vehicle here. Okay, but see, it all depends on how close the start and the goal locations are. Okay, so location means, it means X, Y, and theta. Theta is very important. See, car can be parked in the other, see, with the same position, car can be parked in this direction, right? So in this way. So orientation is different, right? So the orientation is also important. So if you look at this case, so there are three scenarios being shown. See, wherein suppose the car or the robot, it can be, initially the robot is at this position. The car is parked like this. And the car has to move to this location in this orientation. So what is to be done? It has to take an initial circular segment like this, and then a straight line segment, and then a circular segment, so that it will be reaching this orientation. And next, as well as position, see, position as well as orientation I need to achieve. So similarly, initially, if the position and orientation is like this, and the desired orientation and position are like this, you may have to take a path like this. And suppose if they are very close, and see, this is the initial position and orientation, and this is the desired position and orientation. So you need to take closer circles like this and reach this destination. So the key takeaway from this slide is that, see, if you have a robot or a car-like vehicle with turn radius constraint, so generally, except omnidirectional robot, all other robots are having a turn radius constraint. So that means you cannot move the vehicle sideways. So in all those scenarios, you can use these combinations, the combination of circular and straight line segments, in order to move the vehicle from start position and orientation to the destination position and orientation. And how this is achieved? This can be achieved either by using the kinematic model or the dynamic model by driving the vehicle to, so suppose if it's a differential drive robot, you will be driving the robot by feeding in the left wheel, the respective left wheel and right wheel velocities, so that the robot will be moving from this position to this position. Okay, so it's just a combination of straight line and circular segments. So if you know how to move a robot through a straight line, or how to move the robot through a circle, okay, so you can use a combination of those segments in order to get any realistic path in the environment. Okay, so the thing is that you should know how okay, suppose if I have to move the robot, if I have to move the robot through a circular path, for example, if I have to move the robot through a circular path, I should know, okay, my task is, I have to move this, what should be the right wheel and left wheel velocity? So, all with respect to time I need to find, but I should know what should be the x of t for the robot, y of t for the robot. Okay, so have you ever imagined, say, taking a circular path? See, so suppose if you are driving your car and you need to take a circular path. Okay, what should be the x position, x profile and y profile of your car? Have you ever imagined like that? So we need to know all these things. Then only we'll be able to plan the path accordingly. See, your car is to be taken through a circular path. Okay. So for that, I need to find what should be the left wheel and right wheel velocity. In the cars, see, car is a different system. The inputs are not like this. It is actually the acceleration input, the brake input, and the steering. Okay. So for example, the accelerator can be kept at a constant position and or a fixed position, and then steering can be changed. So I can get a steering profile, right? Steering angle profile I can find corresponding to this. But if I need to find that, I should know what should be the xt and yt profiles. Can anyone say if the car has to take a circular path, what should be? So if you plot xt, see, suppose if I am marking this as a ground. So maybe I'll draw it again. This is the ground, this is the x. I'm imagining x-axis and y-axis like this. And the car is taking a circle like this. And what should be the xt profile? And what should be the yt profile for the car? Am I audible? Are you people there?
Yes, ma'am, you're audible. No one has responded.
Yes,
Okay.
yes, ma'am. Yes, ma'am. You are very audible.
Okay. So only if you know what should be the see. So this is actually what we are trying to do. Is I should know what should be the reference x position profile and reference y position profile, so that I can track my car through this path. See, only if I know the reference, I will try to follow this. So that following means my actual car position, xt, yt. So I need to know, right? Then only I'll be able to drive the car like that. So x reference should be no answers. So it can be sin t, cos t. So if you take like this, see, if I decide to have a circle, see, imagining this x as this as the x-axis and this as the y-axis, you will be able to take the car like this. You see this. So in this case, what will be the radius of the circle? If I choose this as the input, see, xrt and yrt. In ground, what will be the radius of the circle? If I take sin t and cos t, so radius will be 1 meter. So if you wish to take a circle, see, generally, using with car, we won't be able to take a circle of 1 meter, 1 meter radius. So because the generally car turn radius will be greater, right? So suppose if you need 2 meter or 3 meter, what will we do? So you will take the reference input as 3 sin t, 3 cos t. So then the same with this point as a center, you will be able to get a bigger circle if you take this as the reference. The only thing is that in order to follow this path, you need to find what should be. See, car I was telling because it is easier for you to imagine, but the same thing, no, if you have a robot near you, and if you ask that robot to take a circular path like this, which is having 3 meter radius. So what you need to do is you need to give the XR as equal to like this and YR like this. And for tracking this, what should be this is the reference I need. And I know the input-output relations. And what I'll do is I will find what is left wheel and right wheel velocity so that it will take a path like this. Okay. And in addition to that, suppose if I need the circle to be somewhere here at a different center point. So earlier, no, here 0, 0 was the center of the circle. So here, suppose if it is 3, 3 is the center, or let it be 4, 4 is the center of the circle. So then what you need to do is you need to give the reference as 4 plus 3 sin t and 4 plus 3 cos t. So it's just a matter of you need to identify, see where the robot is to be moved. Okay, or the vehicle is to be moved, and what should be the the straight line segments. It is easy. You will be able to represent. You know how to represent straight lines, right? So you can represent straight lines easily. And similarly, you should know what should be the circular profile and what should be the radius and where where the sender should be located. So if you know that autonomously, you will be able to drive the vehicle to the desired path. Okay, and see what I was explaining so far was one method of mathematical modeling. See, from the basic physics, you will be getting the standard differential equations, and from that you will be able to derive the transfer function and the state space model. There are alternate options also. So alternate option is that so I'll just go through the slide. See, in order to avoid manual tuning of system parameters, we can use machine learning methods to approximate the physical system. So that means, see, even though we are modeling the systems using the basic physics and all, see, there are always uncertainties hidden in that, right? So there can always be some noises present in the system which will not be, see, there will be always some unmodeled dynamics in the system, right? So if the mathematical model can approximate the physical system accurately, model-based control mechanisms can be derived to optimize the process at the execution time. But sometimes, if you have that model, please go with that. But sometimes, no, it may not be the case, right? It will be a complex system. So then it is better to go with the machine learning based model. So what you need to do is, you should have a set of design experiments. Okay, see, I have a robot. Okay, so already that robot is available to me, and suppose you purchased a robot from a vendor, standard robot you purchased, and you are trying to derive the mathematical model. So what you can do is that you can just move the robot through random paths or standard paths, and you can try to get a set of measurements. Okay, so you can try to get set of measurements, and from the set of measurements, so you will be having what are the inputs given, you will be having what are the output positions of the robots you got. So you have the input output data, and then you train that model using machine learning and all, and then you try to get the mathematical model, or you try to get some model from this using this method. Okay, so this is an alternate way of representing the system. Instead of working with trial and error based methods, either try to work with physics-based models or try to work with this machine learning-based models. So in machine learning model, after taking measurements according to the sampling scheme above, the scheme, the system is modeled based on this data. So based on this data, because we cause the physical system as a continuous vector valued function fx from the system input. So that means, see, you have the set of data as x, okay, and we have the set of if you need to actually find f of x, okay. So you need to find what is f of x. So you know what is x given to the system, and you know what is the y you are getting from the system, and but always there will be some random noise associated with that, that will, which is corrupted by random measurement noise. So you can say that the model you get will be equal to f of x plus epsilon, or whatever variable you give as the random measurement noise. Okay, so ultimately, if you are going for machine learning based models, you will be deriving the model in this form, y equal to fx plus epsilon. So there are many ways in which you will be able to interpolate the data and find y is equal to a fx plus epsilon format. See, I have not worked with this kind of modeling, but I know there are people who are working with this modeling in order to get in order to start working with those systems. So, so those who wish, they can explore in that domain. So before concluding, so this is actually the conclusion slide of the presentation. So if you really wish to design a robotic system, it's always better to start with the kinematic and the dynamic modeling of robots. And depending on the requirement, maybe if the payload is less and the speed of the vehicle is, or the robot is very less, then you can go with the first method, the kinematics based design method. Or if the payload is high, then you should definitely go for this dynamics based modeling. And the next part is actually when we are planning paths, then also don't go for a trial and error based method. So once you have these models, you have the profile for x of t, y of t, theta of t, and try to plan the path for the robot. And see, all these points I have mentioned, and the model can be linear or non-linear depending on the way in which you are modeling. To start with, maybe you can begin with see very simple linear models also, and then you have to see, once the model is ready with you, you will be able to control these robots so that you will be able to achieve the desired task can be implemented with the help of these robotic systems which you are designing or working with. So with that, I conclude my presentation. So if there are any doubts, I'm ready to answer.
Thank you, ma'am. Thank you for a very valuable session. Ma'am. Hello, ma'am.
Yes, I'm here.
Ma'am, can you please tell us the difference between mathematical modeling and state space modeling?
No, you see, state space modeling is one form of modeling only. See, there are different ways in which you will be able to model a system. One is, see, I was mentioning, right? One is transfer function based model. Another one is, see, you can see, whenever you are modeling, you will be starting with the basic equation like this, as I was mentioning. For a very simple system, a block like this, okay, which is being moved like this, I'll be representing this as Oh, okay, I'll write like this: m into d squared x by dt squared plus b into dx by dt plus kx equal to the applied force. So this is how we start. This is one way of modeling the system. The second, so this is all comes under mathematical modeling only. Transfer function is the second way, wherein I'll be representing the same system as the Laplace transform of output it should be. So output is x of s by in f of s is equal to some model I'll get. And state space model, so this is also I'll be deriving from the same equation only. Okay, so and here I'll be writing as x1 dot is equal to x2 and x2 dot is equal to, so some equation I'll get. So if you wish now, I can derive the full model, but this is how we do. Okay, all these are coming under mathematical modeling only. These state space modeling is one form of mathematical modeling only. That's it.
Ma'am, another question. What method is best for dynamic modeling?
To start with, no, the Lagrange-Euler method is the easiest one. You need to find the kinetic energy, potential energy, and you use the standard equation for deriving the model. And there are other methods like Newton-Euler method also, which is a recursive relation, which generally I have seen the mechanical people are very much into that. So, but being from electrical background, I'm very much comfortable with this method. So I generally go with this.
Ma'am, there is
Yes.
another question. In which areas of the industry the development of robotics is currently the most dynamic?
In which areas? Yeah, so what I have seen is many of the researchers are working mainly in mobile robots and aerial robots. Many of the researchers are working in that. But so industries now, many of the robots are, in industries, manipulators are all kind of saturated. So majority of the developments are happening in mobile robots and aerial robots, I should say.
Ma'am, can you suggest some textbooks?
Textbooks to know the basics. So I am generally following Schilling's textbook. Let me take the. It's robotics analysis and control by Schilling. So that's the main textbooks which I am referring to. And there are a lot of, then there is one textbook by Saha, which is also, I think Saha, Professor Saha is a mechanical engineer. He has given the basics very beautifully. That is another good option to start reading or start studying robotics. And there is one more question.
Ma'am, there is a question in the query. Do you think robotics would make an impact in health sector in India?
Yes, definitely. See, nowadays, many people are trying to see in Kerala. If you look at, there is a team called the Breath of Hope. They are working voluntarily for helping doctors. They have developed so many products which are trying to help doctors. So they have developed some. It's not robotics, I should say. It can be automation, so automated products or robotics. Definitely will definitely have a major impact in the health sector. So But the thing is that no, if you look at the number of robotic companies coming up in India, you can't see many. Only few companies are excelling, and so in that way, I think the days are yet to come for robotics. So maybe when the students graduate from when the first batch of students graduate from KTU in robotics and automation, maybe so it's actually now, no, see, if you look at the number of robotic engineers requirements in the industry, specifically it is less, I should say. More of automation engineers are required, but I hope that definitely the scenario will improve, and there'll be a requirement of more robotic engineers, and more robotic projects will be taken up, and products will also be coming up, I think.
Ma'am, I think there are no more queries.
Okay.
So we'll wind up the session.
Okay.
Okay, ma'am. Thank you very much for a very informative session. So we are winding up the session now. The next session is scheduled at 1:30 p.m. Thank you, ma'am.
Yeah, thank you for joining the team. Thank you. It's a good opportunity that, see, I think, but the participants are not at all interacting. It's like, I don't know.
Disha, ma'am, Disha, shall I interrupt you, ma'am? Yeah. Ma'am, the session was very good because the participants, what we have, they are from different backgrounds, from electronics, electrical, instrumentation, mechanical, and different backgrounds. And many of them might not have been working in this field also. So many teachers have joined in the interest of knowing what these things are. And your session, what you have given, is actually a great kickstart to this robotics field, because you have you've actually started your presentation with a few examples of few robots, and then you have also given some examples of line following and pick and place and all, and then you've said why you need a model, what is the importance of modeling. So everything has been very beautifully said, like kinematics and dynamics. So you have introduced everything with very, very simple systems. So I think all those who have joined might have surely thoroughly enjoyed your session. Might be because the questions they did not have, because they have not worked in this area. So, ma'am, the session was very good.
So
Deepa ma'am.
Yes.
Yes,
Deepa
ma'am.
Deepa ma'am, how are you, ma'am? Fine.
Yeah, good. Thank you.
Disha ma'am, I am Vasudev. I have actually completed my MTech in robotics and automation from Amrita University.
Okay.
So the thing which I want to add on to you is that now basically the health sector is booming up with robotics. If you have not noticed, there is 2-3 companies who are actually coming up with very good ideas with mobile robotics, as well as in drone sectors, where they used to sanitize the whole hospital. If you can check it out, IV Tech. It's
I have seen the Asimov Robotics was trying to.
Yes, ma'am. And also, ma'am, how good? I want a small clarification on the presentation that I've taken. How good is inverse kinematics that can judge the dynamics of a robotic system? Is it best way to actually take up the inverse kinematic model of a dynamic system and then work upon the path planning and trajectory planning?
No, it depends on the requirement actually. See, suppose if you wish to plan a robotic manipulator, the end effector path is to be planned, right?
Yes, ma'am. Yes.
So end effector path is to be planned means, so you should know, right, what should be the joint angles, so that theta 1t, theta 2t, theta 3t, so that the end effector will be following some particular path, or so that I can accomplish a task.
Okay.
So if that is the scenario, definitely you should go with this inverse kinematics.
Okay, so not only the manipulators, now inverse kinematics can be applied in a very large scale for even mobile robotics as well.
Yes, sure.
according to the recent development in robotics, they have actually implied in mobile robotics also. The Boston Dynamics company have actually made a robot which bounces from ground level, and they have raised to 10 feet high, 10 to 12 feet high.
Yes, the thing is that so in our in research labs in our universities, so what generally happens is, see, one team of students will be working in a particular project and they leave. So what we need to do, the same project, if the upcoming batches are also working, we'll also be able to come up with very good projects. So if you talk about the inverse kinematics of mobile robots, see, I was also mentioning about the differential drive robots. So if you try to find left wheel and right wheel velocities in order to get the required path, so that is actually inverse kinematics, right?
Yes, ma'am. True.
Knowing, yes. So depending on the requirement, you need to see. I won't say that you should take up the very complex model, but start with a simple model. Try to get the input-output relations so that without trial and error, you will be able to design robotic systems. Okay. That's the main message I wish to give is that many of the students which we see, they are hesitant to learn kinematics and dynamics part, and they say that, okay, do I need to study these things, kinematics and dynamics? So they think it as some hobby. So they consider this as a hobby project, and they are not interested to learn that part.
True, ma'am. Even when you start learning, kinematics is a very simple part, but the inverse kinematics is quite difficult, and it is very hard to crack inverse kinematics. Even I've
what we
worked
need
3
to do
years
is
in
start with a very simple robotic configuration, try to
ma'am.
understand that concept, and then try to take up complex robotic configuration.
True. I've been in the industry for 3 years. I was working for India's first robotic museum at Gujarat. It will be up and running from this coming February onwards. So there we have developed so many models as well as sculptures to study how the robotics have started and how it is still going on and how can be moved further. And I wish everybody to please do have a look on it.
Yeah, that's good. So generally the trend we see in robotic companies that we see the students who graduate from robotics and automation. So then if you compare to the number of job opportunities in automation, the opportunities in the robotic side seem to be less, right? So what I feel is that in the upcoming years, definitely there should be some boom in that part also. Maybe you will be able to add on to that.
Sure, ma'am. We are actually trying our level best.
Yeah. Okay, then. Thank you all for the patience.
Thank you, ma'am.
Yeah.
Thank you so much.
Okay.